The Debate, where we delve into the core of complex issues arising from significant works that have shaped our understanding. Today, we turn our attention to one of the most transformative papers in the history of mathematics, Bernhard Riemann's seminal 1859 work on the number of primes less than a given magnitude. This paper, well, it undeniably inaugurated a new era in number theory, charting a course that continues to challenge and inspire mathematicians today. Our central question, the crux of our discussion, is this. Was Riemann's paper considered epoch-making primarily because of his revolutionary methods and these visionary conjectures he put forth? Or was its enduring impact rooted more in the specific results and frameworks he presented, even if their initial proofs were incomplete? I'll be arguing that Riemann's true genius lay in his groundbreaking mathematical methods and the profound theoretical questions he posed, which fundamentally reoriented the entire field.
And I'll be taking the position that while the methods were certainly ingenious, absolutely novel, the paper's unparalleled significance stems more directly from the concrete formulas and the powerful explicit approximations it offered for understanding the distribution of prime numbers. So my focus will be on those tangible analytical outcomes that really propelled the field forward.
To my mind, Riemann's paper marks a pivotal, almost, seismic shift in mathematical thought. It wasn't merely about adding new facts to an existing ledger, but rather about introducing an entirely new paradigm for their discovery. Before Riemann, primes were often studied in a more, let's say, combinatorial or elementary fashion. What he did was fundamentally different. He brought the full force of complex analysis to bear on their distribution. The very fabric of his approach, studying the zeta function, zeta of S, but crucially extending its definition to a complex variable, that was a profound leap. Instead of just thinking about real numbers, he started exploring this function across the two-dimensional complex plane. In this abstract move, it unlocked incredible hidden properties of the function that were directly linked to primes, a connection nobody had really conceived of before. This involved looking at its complex zeros, the sophisticated use of Fourier inversion techniques, and developing what he called explicit formulas connecting these tools back to counting primes. These were the real epoch-making contributions. Historical analyses often highlight this, with many scholars noting, and I quote, "The real contribution of Riemann's 1859 paper lay not in its results, but in its methods." And it's incredibly telling, isn't it, that for almost 30 years after it was published, the mathematical world seemed almost stuck regarding prime number theory. There was virtually no progress. It's like mathematicians needed that time to really digest Riemann's ideas, to grasp this entirely new language he'd invented. Only after this period did giants like Hadamard, von Mangold, and the Lavalley-Poussin used Riemann's ideas, his complex analytic framework, to rigorously prove his formulas and, importantly, the prime number theorem. And furthermore, the Riemann hypothesis itself, this profound conjecture coming straight from his methods about the zeros of zeta, well, it's become the most celebrated problem in mathematics. Its very existence, the quest for its proof, demonstrates the lasting power of his visionary, method-driven insights to inspire new techniques and far-reaching importance, even without him providing a complete initial proof.
Okay, while I readily acknowledge the sheer novelty and, yes, the theoretical elegance of Riemann's methods, I find myself compelled to emphasize that the profound impact, the thing that really makes it epoch-making, ultimately resides in the specific results and the powerful, explicit framework he provided for understanding prime distribution. I mean, just look at the paper's title, On the Number of Primes Less Than a Given Magnitude. That's not a title hinting at abstract methods. It points directly to its goal, provide a formula for pi of x, which, counts primes less than x. That was the driving force, the practical mathematical problem he was tackling head-on. Indeed, the source material says, the principal result was a formula for pi of x as the sum of an infinite series in which integral 2x dt log t is by far the largest term. Now, this integral 2x dt log t, that's the logarithmic integral, LIX. which is this standard, increasingly accurate approximation. Riemann's explicit formula for Jx, and from that for pi of x, led to an approximation that looked roughly like pi of x approximately Lix 1/2 Lix to 1/2, 1/3 Lix to 1/3, plus ... And what's crucial here is that even if it wasn't fully proven to modern standards right when published, this approximation was empirically stunningly illustrated by Lemur's tables, these detailed prime counts. For instance, take x equals 1,000,000. Riemann's approximation had this remarkably small error of just 30. That's a huge improvement compared to Gauss's earlier, widely accepted approximation, which had an error of 130.
This tangible, quantifiable improvement in approximation, plus the clear, explicit, analytical connection he forged between zeta sense and primes through the Euler product formula and everything that followed. That, to me, is the essence of the relationship. That's what truly made the paper revolutionary. It provided concrete, verifiable answers that moved the needle decisively.
I can certainly appreciate the allure of those stunning empirical results, and I see why you'd prioritize that tangible accuracy. But I think we need to dig a bit deeper into what constitutes the real contribution here. While the approximations were indeed impressive, historical analysis consistently points to the idea that, and again, the real contribution lay not in its results, but in its methods. It wasn't just about finding slightly better numbers. It was about changing how we find them, about building an entirely new conceptual machinery. The framework of complex variables, the zeta function viewed on this complex plane, the functional equation connecting its values, these were the lasting intellectual tools, not just the sort of temporary answers they yielded in 1859. Riemann's approach was a conceptual breakthrough. It fundamentally reoriented the study of primes, giving us a completely new lens. Think of it like this. Maybe previous mathematicians were trying to count stars with the naked eye, perhaps with a very basic lens. Riemann, though, he provided the blueprints for a vastly more powerful telescope. Those are the methods allowing future astronomers, or mathematicians in this case, to map the cosmos in ways previously unimaginable, even if he himself only got the first few, maybe slightly blurry observations. The real innovation was in the conceptual machinery he built, the new paradigm it established for number theory.
Well, I understand the argument for the profound conceptual shift, I do. But I find it challenging to just accept the premise that the results were secondary, or, merely a byproduct. If Riemann's paper had presented these revolutionary methods, this new telescope, as you put it, but failed to deliver any compelling results or significantly improved approximations for prime distribution, would have it had the same immediate and lasting impact? I'd argue probably not, or at least not nearly as quickly. The methods were developed, in a sense, for the purpose of finding these analytical formulas for pi of x. The essence of the connection between zeta s and primes, as our background material notes, is fundamentally the Euler product formula. Now that formula, which states zeta s equals a product over all primes, that's a powerful result. It links the two domains. It's not really a method in itself, it's a specific foundational mathematical statement. The methods, incredibly ingenious as they were, provided the path to articulating these profound relationships and getting these quantitative estimates. It was these powerful numerical results, the dramatic improvement over Gauss's approximation, that provided immediate validation and drew intense scrutiny and, frankly, excitement to the work. Without those really compelling outcomes, the methods, however elegant, might have remained obscure for even longer, perhaps delaying that digestion period you mentioned for decades more.
That's a fair point about the immediate practical impact, and I don't dispute the empirical success. But that very success, achieved without full, rigorous proof, kind of underscores my point. The true enduring contribution was the framework he provided for proving such results later, a framework others then had to master and solidify. Consider the rigor, or maybe the initial lack of rigor, in his actual proofs. The source material is quite explicit here, stating that Riemann's proof of this formula was inadequate, and that it was by no means clear from Riemann's arguments that the infinite series for pi of x even converges. This highlights something crucial. The methods themselves were the robust, innovative aspect. They were the theoretical bedrock. It required subsequent mathematicians decades later to rigorously establish the validity of his stated results. So the strength wasn't in his initial, maybe somewhat heuristic deployment for specific conclusions, but in the grand theoretical machinery itself, in the audacious vision of using complex analysis where no one had really gone before. Even for something as fundamental as the number of roots of the zeta function in the critical strip, his proof was simply to say it, apparently giving no hint whatsoever of the method he might have used. This strongly suggests the methods were the core intellectual gift, a rich theoretical landscape waiting for others to fully explore, clarify, and build upon. The results were these tantalizing glimpses of what the methods could achieve rather than fully realized, self-contained contributions right then and there.
That's a compelling argument about the initial lack of complete rigor, and I don't dispute that the full analytical justification for some claims took decades. Mathematical rigor is, of course, paramount. But what I find even more compelling and what I think really defines the epoch-making quality in practice is the astonishing empirical accuracy of his formulas for pi of x. The fact that his approximation was stunningly illustrated by Lammer's data, like we discussed, that's not a minor detail. Let's look at the exact numbers again from Table 3 in the source. At x equals 2 million, Riemann's error was just -9. Compare that to Gauss's error of 122. This wasn't just a marginal improvement, it was a massive leap in predictive power. This predictive capability, drawing directly from the explicit formulas Riemann presented, was a powerful, concrete advancement. It superseded previous empirical observations from giants like Euler and Gauss. It was an undeniable, tangible demonstration that his approach, even if not fully vetted analytically by him at the time, provided answers that were demonstrably closer to the truth than anything that came before. It's this profound practical utility and the improved predictive capability of these results that truly made an immediate, undeniable, and revolutionary impact on the mathematical community, proving the worth of his path forward.
Okay, let's pivot slightly and consider what might be the most celebrated and enduring aspect of his work, the Riemann hypothesis itself. Now, this statement that the complex zeros of the zeta function, the non-trivial ones, all have a real part equal to 1/2, that's not a result, it's a profound conjecture. It stems directly from his exploration of the zeta function's properties using complex analysis, his methods, and how they unveiled the very architecture of this function. It remains unproven today, yet it has become the most celebrated problem in mathematics, a sort of mathematical Mount Everest that has captivated the finest minds for over 160 years. Its very existence and the intense ongoing quest for its proof signify the enduring impact of his methods and the new theoretical landscape they opened up, rather than just a settled result. Its unproven status actually underscores my point. His contribution was about posing these deep fundamental questions and, crucially, showing the mathematical community how to approach them with entirely new tools, not just delivering final complete answers. The pursuit of the Riemann hypothesis and the vast amount of mathematics it has generated is arguably the ultimate testament to the power of his methodological vision, a vision that pointed towards truths far beyond what could be immediately proven back then.
Right. While the Riemann hypothesis is absolutely a monumental conjecture, and I agree its unproven status makes it this incredible driving force in modern number theory, its profound significance, I believe, is intrinsically rooted in what it claims about a result. Specifically, the precise location of the zeta function's non-trivial zeros. This location, if the hypothesis is true, has extraordinary implications for the results related to the distribution of primes. The whole pursuit of its proof is driven by the potential for a deeper, more refined understanding of prime number distribution. Precisely the kind of more accurate results for pi of x and related functions that Riemann was explicitly seeking in the first place. So, while yes, it's a conjecture, its importance lies in the result it would establish about the fundamental nature of primes.
It is therefore a deeply results-oriented quest, maybe the ultimate result-oriented quest in this area, albeit an incredibly challenging one. It speaks to the power of the specific claims he made about the zeros and their direct, profound connection to prime enumeration. The methods were the pathway, sure, but the destination, the result, embodied in the hypothesis, is what gives it such immense gravity.
So to summarize my perspective, Riemann's monumental paper truly redefined the mathematical landscape, not necessarily by delivering fully proven final answers, but by equipping the mathematical world with a revolutionary set of methods and an entirely new language. A language through which to approach the most profound and fundamental questions about numbers. His innovative use of complex analysis, his deep exploration of the zeta function, and the very act of conjecturing fundamental truths like the Riemann hypothesis, well, they laid an entirely new theoretical groundwork. And this groundwork catalyzed decades, even centuries of future research, and continues to inspire mathematicians today. This shows, I think, that the true enduring power lay in the conceptual toolkit he bestowed upon us.
And I would just reiterate that the epoch-making nature of Riemann's paper, for me, lies squarely in the concrete, powerful results and the explicit analytical framework it provided for understanding prime number distribution. The development of specific formulas for pi of x that proved empirically superior, stunningly so, to previous approximations, and the undeniably explicit connection forged between the zeta function and the primes, these provided the definitive problems and, crucially, the initial, remarkably accurate solutions that fundamentally advanced the field. The paper's title itself and the evident utility and accuracy of its approximations clearly underscore this results-driven impact. They provided tangible proof that a new and much better path had been found to illuminate the mysteries of primes.
Well, while we might respectfully disagree on whether the methods or the results represent the primary epoch-making contribution, it is, I think, abundantly clear that Riemann's paper represents an extraordinary confluence of theoretical innovation and tangible mathematical insight.
Absolutely. Whether you lean towards the groundbreaking methods he introduced or the profound, almost prophetic results he presented, the work undeniably illuminated our understanding of prime numbers in completely unprecedented ways, and it certainly left and still leaves much more to explore within its rich and complex material.
Welcome to the